This is section 1.2, functions and function notation. And this time we're going to be looking at our functions from a graphical approach. So last section we were looking at tables of values and ordered pairs where all of our data was numerical. Now our data is going to be graphical. All right, when we look at a graph, our input or our independent variable is always going to be on the horizontal axis. So in this particular case, as I look at example 1, the graph is showing the price per person of a ski trip based on the number of people who go on the trip. And you'll see that my horizontal axis here is kind of small, but it's labeled N for number of people. The output, that is the dependent variable, is always going to be represented on our vertical axis. And in this example, again, showing the price per person of a ski trip, you can see the vertical axis is labeled with a P for price. You might have to squint a little bit. Sorry, that print got a little small. Keep in mind, again, a graph represents a function if each input has only one output. So let's look at our little ski trip graph here. And the first question is this the graph of a function? And let's see, I'm going to say yes. Every input, for example, here when, I'm going to make this a little bigger, when the input is 4, the output looks like it's 1400. Or this would be 7 right here, right? And the output looks like it's about a little under 1,000, and so on. But if you look up, every single input has just one output. And again, that makes logical sense in the context of this situation. It wouldn't make sense if we were charging different people different prices, or at least hopefully it wouldn't make sense. So I'm going to say yes. Each value of n has only one value of p. And again, that's our typical explanation for a function, that every value of the input has exactly one value of the output. All right, the next question, is this discrete or continuous? Well, let's see. Our graph is showing values just for whole number inputs, 4, 5, 6, 7, and so on, right? Would it make sense to have the other inputs, like fractions and decimals, 4.5 or 6.2? And in this case, I'm going to say no, right? The n is the input is the number of people, and you can't have a part of a person going on a ski trip. So I'm going to go with discrete. Oops, discrete. And must be a whole number. Cannot have an input that's a fraction or a decimal here. All right, identify the variables and write this in function notation. So we've kind of mentioned it already, but I'll say it again. Horizontal axis, my input, n is the number of people going on the trip here, and my output p is the price that they're going to pay. Writing function notation, we always start with the output variable. So p equals, and it's going to be a function of n. You can choose your own letter. I'm going to use the output letter, p of n. Again, you could write that as f of n or any other letter that you want to call it. I like to remind myself that that output is a p, a price. Okay, let's look at the pattern here just a little bit, and then we'll start answering some of the other questions. It looks like the more people go, the smaller the price per person is. And hopefully that makes sense, right? If they're sharing a bus or whatever, they don't have to pay as much per person if they are splitting it more ways. All right, find P of 5 and explain what it means. So looking at P of 5 here, when the input n is 5, the output is 1200. So I'm going to say P of 5 equals 1200. And that means that n, the number of people, is 5. So when 5 people go on the trip, the price per person is $1,200. All right, the next question, find all values of n so that P of n equals 800. So this time we're finding n. The 800 is the value of P. So I'm going to come up here to my graph and I'm going to say, well, let's see. There's 800 for P. And if I follow that over, it corresponds to that point right there, which had an n of 10. So my n is 10. And interpreting that, n is the number of people, so when 10 people go on the trip, they've now cut their costs to $800 per person. All right, the last question is to find the domain and range of P. And we're going to have to make a few assumptions here. First of all, as far as domain and range, we are going to be using discrete values, right? This is not a continuous function, so that means I'm going to list them. And it looks here like the smallest number of people that can go on this trip is 4, right? There were no outputs, no prices for 0, 1, 2, or 3 people. So probably the bus company has a minimum or something like that. At any rate, we can't have less than 4 people. So the number of people, the input, would be 4, 5, 6, 7, and so on. And that's going to comprise my domain. Again, remember domain is the values of the inputs. Now, is there an upper limit? Well, there probably is, and in fact, we have a couple of options. If we don't think we know, we could just simply leave it as ... But I will notice here again in my graph, it looks like once I get to 16 people, when I look out at 17 or 18, there's no dots again. So perhaps the capacity of the vehicle they're taking is no more than 16 people, and it looks like that's going to be my largest number of people that can go on this trip. So I'm going to say my list here for my domain ends at 16. All right, what about my range? These are my outputs. And let's see here. It looks like the largest value is up here at 1,400. Oops, sorry, you can't see that. Up here at 1,400 is the most per person that they would have to pay. And the smallest down here at 1,600, oh, let's see, it comes in right here. That's 600, 650, 7, yeah, that'd be 650. Looks like my points are all, or my divisions here are in 50s on the way up. So I'm going to say they'd have to pay between $650 and $1,400. Now, a couple of things about how I've listed that. I could go through, and if I had the time, and I don't want to take your time to do this, I could actually have listed literally every single value in here because they are discrete. but there's no specific pattern that's obvious, I don't think. And so rather than showing a pattern like I did with the domain, right, it's every whole number, 4, 5, 6, etc., I simply listed the smallest and the largest. I didn't list them continuously. I didn't do the inequality notation because it isn't possible for the range to hit every single value between 650 and 1400, but some specific values between there are certainly allowable. And again, if you wanted to take the time, you could actually read all those specific values off the graph and list them. I'm choosing not to do that because it's a little boring to watch. All right, let's take a look at another example. All right, so here's another graph. And in this case, the graph is showing the height of a ball that's thrown into the air. So notice this ball looks like right here is a height of 5. The ball's thrown upward, so it goes up. And then as time goes on, it comes back down. And it lands on the ground again. Looks like about there. Right? So again, is this the graph of a function? Well, let's see. If I have any particular input, like say x equals, or actually this is t equals 0.2 seconds, there's just one output. And that's true for all of my inputs. Every input appears to have just one output on the graph. That also makes sense. At any time, how many different places can the ball be? Well, just one. So I'm going to say yes. Each value of t gives only one value of h being the height here. All right, is this one discrete or continuous? Well, this one, you can actually see it in the graph, is continuous, right? I don't have separate dots, I have one continuous shape. And again, it also makes sense. Time isn't split up into just 1 second, 2 seconds, 3 seconds. You can have parts of a second. You could have 2.5 seconds or 3.9 seconds or whatever. So this one is continuous. Values of t can be fractions, decimals, etc. All right, identify the variables and write the function notation. So let's start with our input. Input is always the horizontal axis. In this case, that's t. And that is our time in seconds. Output is always our vertical axis. And that's the height h given in feet. So if I want to write function notation for this, I always start with my output variable. So h equals, and that will be a function of the input t. I'm going to write h of t, but if you choose a different letter for your function notation, that is certainly fine. All right, the next question. Find h of 0.5 and explain what it means. Right? The 0.5 is the t value. So I'm going to go up to my graph and I'm going to find t equals 0.5 and I'm going to see what height that corresponds to. So let's see here. 2, 4, 6, oops, halfway between 4 and 6, there we go, would be 0.5. And I'm looking up at the graph, and looks like I'm all the way up here at the very highest point that this ball ever gets to. Corresponds to that h value, which is halfway between 8 and 10, so it must be 9. So h of 0.5 is 9. 0.5 was the time, so at or after 0.5 seconds, the ball is going to reach a height of 9 feet. All right, the last question on this example, or excuse me, I guess this one goes to the next page. The next question, find all values of t so that h of t equals 5. So this time they gave us the h value, 5, and our goal is to find the t that goes with it. So coming again back up here to the graph, here's my h equals 5 right here, and I can see immediately that at time 0, h is 5. But if I were to follow on over here, it happens again, right? H is also 5 over here. And that looks like that happens at exactly t equal 1 second. So at t equals 0, I have a height of 5. And at t equal 1, I also have a height of 5. So first of all, to answer the direct question, t equals 0 or t equal 1. And in terms of what that means, the height of the ball is 5 feet at time 0 seconds and at time 1 second. Not too surprising, right? Basically at 0 seconds, it's when we first launched it upward, and then it came back down through that same height after 1 second. All right, I'm going to keep that graph handy. We may need it again. And we are going to take a look at part F. All right, F and G are actually the domain and range. So let's take a look at those. This is continuous, so I am going to want to use the inequality notation here. Domain, again, is the inputs, and we'll take a look at those first. So on my inputs, the smallest time would be 0 seconds. Kind of makes sense, right? You wouldn't want a negative time. And the largest time here on the graph is when the ball lands on the ground. And let's see, what have we got here? That would be 1.2, this would be 1.3, so that must be 1.25. So I'm going to say my times range from 0 to 1.25 seconds. That's my domain. And as far as what it means, essentially we threw the ball at time 0 and it landed at time 1.25. So it took a total of 1.25 seconds while that ball was in the air. All right, we want to find the range, the outputs. Range, the outputs will be the vertical axis. So I'm looking at these. And let's see here, my heights, the smallest height I'll ever have is way over here when the ball lands at a height of 0. And it looks like the largest height this ball ever reaches was that 9 feet that we looked at. So I'm going to say my heights go from 0 to 9. All right, that means that the ball's height is always, always, can't spell here, less than 9 feet. It's always greater than 0, but sometimes some things are sort of obvious, right? Your ball wouldn't have a negative height, so I didn't bother stating that. Okay, we have a couple more definitions here, new definitions. The next one is the intercepts. The intercepts of a graph are the places where the graph crosses the axes. They're often kind of special. They often have particular meanings or interesting applications, so we're often very interested in those intercepts. And I'm going to start here with the h-intercept. This is where we cross the h-axis. Intercepts I typically list as an ordered pair. So when I look at the h-axis, right there is where the graph hits that h-axis at the point 0, 5. So I'm going to list my h-intercept as 0, 5. And explaining what it means. When the ball was first thrown at 0 seconds, it was thrown from a height of 5 feet. One of the things that I want to encourage you, and I've mentioned this before, but I'm going to say it again, is when you're asked to interpret or explain what something means, give me full, complete sentences, really explain it. You are convincing me as your reader and the person who grades your paper, you're convincing me that you understand everything about this. So tell me everything you know about what that point says. All right, the other intercept, our t-intercept, or where the graph crosses the t-axis. Let's look back at the graph again. And that's right there, right? The t-axis. Right there we've got our graph hitting that t-axis, and the t-value, we kind of identified it for a previous question, was 1.25. So that point is actually 1.25, comma 0. So at time 1.25 seconds, the height is 0, or in other words, the ball is landed on the ground. All right, I'd like to say just a little bit more about these intercepts because there's something here that we're going to continue to use, something very important actually that we'll use all throughout the course. Take a look at those intercepts one more time. When I wanted the h-intercept, Notice the point had a t value of 0, right? This is t comma h. And when I wanted the t-intercept, again, this is t comma h, the h value is 0. This is typical, and we're going to see it over and over again with our intercepts. Whatever intercept you're looking for, the value of the opposite variable ends up being 0. So with the h-intercept, the t value is 0. And with the t-intercept, the h value is 0. Again, we'll come back to that. We'll use that really throughout the entire course. All right, one more definition associated with this example. A graph can have what's called a local maximum, which is sort of the top of a hill in the graph. Or it could also have a local minimum, which is kind of like the bottom of a valley. We'll see both as we look at more graphs, but let's talk about what this graph has, give the coordinates, and explain what it means. So in this particular graph, this point here, which was 0.5, comma 9, is sort of at the top of the hill on the graph. And so it's going to be a local maximum. It's actually the largest y value on the graph. And the coordinates then of this local maximum were 0.5, comma 9. When you explain what a local maximum, or later what a local minimum is all about, when you interpret it in terms of the situation, you always want to mention something specific about it being the largest or highest point or lowest point. So in this case, in the interpretation, the ball reaches its highest point, 9 feet, at time 0.5 seconds. And so you'll see I get that little extra idea in there about the maximum being the highest point. I didn't just say at 0.5 seconds it reaches 9 feet. I specifically mentioned that 9 feet was the highest point that that ball ever reaches. All right, we are ready to move out of that example and into the next. And we're going to talk a little bit about what's called the vertical line test. This is something that you've probably seen before. We just haven't mentioned it yet in this class. So let's take a couple of minutes and do that. This is one way to check to see if a graph represents a function is by using what's called the vertical line test. Here's the vertical line test right here. It says, a vertical line only intersects the graph of a function in one point. If your vertical line, if any vertical line, intersects in more than one point, then we don't have a function. Let's think about why that makes sense. And I'm just going to go back one more time to that last example and talk about it. We already said this was a function. But why does the vertical line test work? Well, if I were to take a vertical line somewhere and just draw it, I'm just going to pick a random spot here, draw a vertical line, you'll notice it only hits the graph in one point. Why does that have to be true for a function? Well, a vertical line represents a very specific input, or x value. And that x value, or in this case it's actually a t, I guess, that input, whatever it is only allowed to have one output. So that vertical line is all the same t value, it better only have one output. It better only hit the graph one time. Of course, if I were to go along here, I would see that that's true no matter where I drew my vertical line. So that would be another argument that said that this graph is the graph of a function. Every vertical line only crosses the graph once. So to answer the question, why does this make sense? Each vertical line represents a value of the input, or independent variable. It's only allowed to have one output, so it can only hit the graph once. So in a function, this input can only have one output. Or in other words, it can only hit the graph once. All right, we already looked back at our previous example, which was actually example 2, and showed that it passed the vertical line test. If I go back real quick to example 1 with the ski trip, once again, if I were to draw any particular vertical line, like say here at 6, it only hits my graph one time. Notice that every vertical line doesn't have to hit the graph, right? If I drew in between my points, I could draw a vertical line that doesn't hit the graph at all, and that's okay. It just can't hit more than once. Every vertical line I drew then, if it hits at all, only hits in one place. So yes, our examples that we've looked at so far definitely pass the vertical line test. We'll talk a little bit more about that vertical line test in just a couple of minutes. I have one more thing I want to introduce here first. This idea of interval notation. So far, when we've wanted to describe a domain or a range for a continuous function, we've generally used inequalities, right? The less than and greater than signs. As you go on in math, you'll find that often, rather than using intervals as less than or greater than signs, we'll use a different type of notation called interval notation. You may have seen this before, but if not, I'm going to introduce it to you briefly right here with this little chart. So let's take a look at this inequality, an x value that's between -1 and +3. To graph that on a number line, I'm going to use a solid dot on -1 and a solid dot on +3 and show that the x's can be anything in between. By the way, I used those solid dots because this was not just less than or greater than. These were actually both less than or equal to's. So the solid dot actually represents the part that allows x to be equal to -1 or +3. We'll see what happens when they're not in the next example. All right, how do I write this as an interval? The first and most important thing about interval notation is that you always read it left to right, every single time. So I'm going to start by writing down my leftmost value, -1. We then use a comma and our rightmost value, +3. Automatically, with interval notation, we assume that all of the values continuously, including fractions and decimals, are allowable between the left and right, the -1 and the 3. You would not use this for a discrete situation, just for a continuous one. All right, I'm now going to put some brackets around this. And the brackets actually represent the endpoints. The fact that I can actually reach -1 is represented by that bracket, and the fact that I actually reach +3 is represented by the other bracket. So what happens if I don't have the little equals piece? what happens if I just have a strict less than, like I do here? Well, my x's here are between 2 and 5, and because 2 is strictly less than x, not equal, I'm going to show that on the graph with an open circle. I can reach 5, right? I can possibly have it equal to 5. So that'll be a closed circle. And then everything in between. Again, intervals always represent continuous situations. So reading my interval from left to right, my values go from 2 to 5. Now this time I need to show that x can't actually equal 2. And I do that with a parenthesis. X can equal 5. So I'm going to put the bracket on that. All right, what about situations where I don't necessarily have a start and an end point? Maybe I just have a starting point or just have an ending point, and x can go on forever. That's what these next two are all about. In the next example, x is greater than -2. So first of all, I'm going to put -2 as my starting point. Think about it. Should I be using an open circle or a closed? It's not equal to, right? Just greater than. So an open circle. Now my x's can be bigger than -2. So all these values are bigger than -2. And they go on forever. So I'm just going to show that on the number line with my arrow here. In order to write an interval for these situations, what you want to do is think about on your number line, the far left end, if you kept on going on forever, could be considered at -infinity. It's not a value we can ever actually reach. It's more of a theoretical idea. And again, on the right-hand end, you'd have this positive infinity. Again, not an actual value that you can reach, more of a concept. So when I go to write my interval, my starting value is 2. And because this really never has a largest ending value, I see it keeps going to infinity. An open circle, so I have a parenthesis here. And because I can't truly reach infinity, I have to have a parenthesis there as well. Infinity will never have a bracket because you can never actually get to infinity. All right, we have one more example here. X is less than or equal to 4. So I'm going to start here with 4. And this time I do have the equals, so it's going to be a closed bracket. Or excuse me, closed circle for right now. And then x is less than or equal to 4. So smaller than 4, going that way. Again, I want to think about -infinity and positive infinity as kind of being at the far ends of my number line. Always, always read your interval from left to right. So -infinity is my leftmost end point, if you will. And I continue to 4, which is my right end point. You'll notice I used the parenthesis at -infinity because I can never actually get there. But because of the closed dot there at 4, I used the bracket. This is the one that is most tempting to write incorrectly. Because the arrow goes in that direction, people like to write that as 4, -infinity, but that is actually not correct. Ignore the direction of the arrow. You always read intervals from left to right. All right, our last couple of examples, we're going to be using this interval notation. And each of the graphs on the next couple of pages are going to be presented with no context, so we'll just default to x's and y's. We'll assume our input is x, the horizontal axis variable, and our output is y, the vertical axis variable. And our goal is to be answering the question, first of all, I maybe didn't even say that. Let me do that. I first want to answer the question, is it a function? We should probably answer that first. And then secondly, we'll give the domain and range, and we'll use our new interval notation to do that. I guess I asked if this is a function here. All right, so here's our first graph. Is it a function? Well, the quick answer is it passes the vertical line test, right? No matter where I were to draw a vertical line on this graph, it's only going to ever hit the graph once. So I can say yes, and by way of explanation, when I have a graph, I can just say it passes the vertical line test, which I like to abbreviate as VLT. All right, we're going to list our x and y intercepts next, and I'm going to say the x-intercept crosses the x-axis right here at 4, 0. The y-intercept is right here. We are halfway between 0 and -2, so that must be -1. So the point would be 0, -1. All right, domain and range. I really need to pay attention here to the arrows. Notice that this graph goes forever up and to the right, and it also goes forever down and to the left. So I'm going to say because this graph goes forever both left and right, the domain goes all the way from -infinity to +infinity. I can make the same exact argument on the range, right? Keeps going down, so down to -infinity eventually. And it keeps going up. So if I looked long enough, I would have to say it goes up toward +infinity. Because of the arrows, this graph does not have starting and stopping points. It keeps going forever. All right, in part B here, we're going to stop real quick on this one because when I ask you the question, is it a function? We're going to have to say no very quickly, right? In fact, if I just sort of randomly pick a vertical line here, you can put it anywhere you want, it doesn't matter. I can really quickly see that there are 2 points where that graph is intersected by that vertical line. And so I'm going to have to say, no, this fails the vertical line test. Okay. Although we could ask more questions about this, we're not going to. If it's not a function, I'm just going to kind of leave it be. All right, our last example gives us this graph. And once again, the first question is this the graph of a function? I want to draw on it later for other reasons, so I'm not going to draw my vertical lines this time, but you can just kind of imagine them, right? If you imagine vertical lines anywhere in this graph, it would only hit this graph in one place at a time. So this one passes the vertical line test, and I'm going to say yes, it's a function, passes that vertical line test. All right, next, list the x-intercepts. There are actually several of them. How many do you see? I'm looking at 3. There's an x-intercept here, here, and here. So let's see, halfway between 0 and -2, so it looks like that one's at -1. Its coordinates would be -1, 0. That one clearly is at x = 2, so 2, 0. And the last one over here at 4, comma 0. All right, listing the y-intercepts. Where does it hit the y-axis? Well, just one point right there. And by the way, notice if your graph is a function, it really is only allowed to have one y-intercept. If it had more than one y-intercept, it would fail the vertical line test, right? All right, where are we at here? 5, 6, 7, 8. So 0, 8 is my y-intercept. All right, domain and range. Once again, I'm going to notice they're up here, right? Little arrows on the ends of the graph means the graph goes on forever. So it goes up to the left forever and up to the right forever. Since it goes left forever and right forever, my domain once again is going to be negative infinity to infinity. But what about the range? It does go up forever, but it doesn't go down forever. In fact, when I think about the output, the y values, there is a smallest y value on this graph. Looks like it's here at negative 17. So when I go to list my range, I'm going to say the outputs are vertical, has a smallest value of negative 17, and then it goes up forever to infinity. Now I always use parentheses on the infinity portion, but what about the negative 17? Well, that graph actually hits the value of negative 17, so I want to include it, meaning I'll need to use a bracket. All right, the last thing we're being asked to find on this graph would be local maximums and local minimums. I'm going to label them now, and then we'll just transfer the information in a moment. So, top of a hill, local maximum. I do see one right about here. Right. Now notice, it's not the largest y value on the whole graph, right? The y values get bigger out here at the ends. But that's why we call it a local maximum. In its own little neighborhood, it's the top of a hill. All right, let's see if I can estimate what that value is. Let's see, this would be 1 right here. So it's between 0 and 1. Let's see, this would be 0.5. I'm going to go with about 0.75. Sometimes you have to estimate when you have graphs. And in terms of the y value, 10, 11, between 12 and 13, I'm going to call that 12.5. Right? If you're not given a graph accurate enough to know exactly, or if the points aren't exactly on the grid, you may have to do a little estimating, and that's okay. Now that's my only local maximum. I don't see any other points that represent the top of the hill. So my local max is just 0.75, comma 12.5. All right, what about local minimum or local minimums? I actually see 2 of those. Right? Local minimum is the bottom of a valley, and there's one right here. This point, negative 1, 0, is the lowest point in its own little neighborhood. It's the bottom of a valley. It's not the lowest point in the whole graph, which is why we call it a local minimum. It's the minimum in its little neighborhood. There's another one over here, another bottom of a valley. This would be another local minimum. And let's see here, what have we got? See, this was 2 and 4, so this would be 3. This would be 3.5. So I'm going to estimate that as about 3.2. Y value, we've actually already talked about that one. Looked like it was negative 17. That one hit my grid line kind of nicely. Now again, if you were doing this like on a homework or a test or something, don't stress. Obviously, if you thought that was 3.25 instead, I can't fault you when you're estimating unless you're way off. If you called that 3.6, I'd have a problem with it. But as long as you're in the ballpark, I'll be okay in cases where you have to estimate. So my two local minimums, negative 1, 0 and 3.2, comma negative 17. All right, that brings us to the end of the section on functions that are defined using a graph. We have one more way to define functions analytically, and we'll look at that in the next section.